starting today, kicking off Meeting C++ 2020 with the first keynote, Jonathan Boccara. I really look forward to your keynote. And yeah, Jonathan is a great blogger, well-known personality, and I'm now really looking forward to your keynote. And with that, please take it away.
Thanks, Jens. Today, I want to talk to you about meta-polymorphism. So what is meta-polymorphism? Perhaps you're thinking about meta classes, and that would be polymorphism on meta classes. And I don't suggest you think about that because that might cause some smoke puffing out of your ears. What we're going to talk about is much simpler. We're going to talk about polymorphism, the regular polymorphism. But polymorphism is about having several ways to do one thing, one interface. And the message I want to get across in this keynote is that there is more than one way to do polymorphism. There are various kinds of polymorphism. So it's like polymorphism on polymorphism, hence the meta polymorphism. Before getting into the details, why is that important? First, let's agree on what we mean by polymorphism. So by polymorphism, I mean there's an interface that can be implemented by various kind of things. I'm saying components because it's a generic term, because as we all see, there are various kind of things that can get into polymorphism. I think it's a pretty good definition because it kind of sticks to the word polymorphism. Now, why is that important? I think polymorphism is at the core of programming. It's been there since for a long time, and I think it's going to be there for a long time again. Why is that so important? Well, if you think about this interface, like a contract, for example, that is implemented by various components. So in this diagram, I'm having components: a square, a circle, a lightning bolt, a rectangle, abstract things that implement an interface, right? And there's a client using that interface that will end up using one of those implementations through the interface without knowing which implementation it's using. So polymorphism allows to decouple two parts of the code, right? It decouples the client code from the implementation. And this introduces modularity. And modularity is perhaps the one thing that is in common in all programming paradigms I've got to see. So this is why I think polymorphism is very important, and it's worth spending time understanding what polymorphism and all we can do with polymorphism. Everything we're going to see is in C++, but I think most of it applies to other languages, and certainly the core message being that there's more than one way to do polymorphism. Certainly applies to many languages. If you think about the various steps that source code goes through on its way to becoming a runnable program, in C++ there are 4 steps: preprocessing, compilation, link, and runtime, right? And if we think about it, when we think about polymorphism, the first thing that may come to your mind, at least it was the way with me, is virtual functions, right? Interfaces, inheritance, virtual functions. And this polymorphism is resolved at runtime. By resolve, I mean the moment where the actual implementation that is going to be executed, it's chosen at runtime, right? Now, there are other moments in the life of source code before runtime, And the first thing we're going to see today is that at every one of those steps, there can be polymorphism. Polymorphism is not just at runtime. Let's start with pre-processing, which may be one of the most surprising. So by pre-processing, I mean, how's defined, right? Before we get into the code, there is a disclaimer that I have to show. It's that macros are bad, except when there aren't. Now, the views and opinions exposed in this talk do not encourage you to use macro or polymorphism with macros unless you're willing to try at your own risks. This talk presents polymorphism in the broader sense and includes macros for the sole purpose of illustrating polymorphism in a broader context, and asserts in no way that macros are always good, always bad, or whether it always depends. In fact, we're willing to assert that macros are not always good, but still, that's not the point here. Now, that being out of the way, let's see what polymorphism with macro could look like, even though this is not something you want to do all the time, obviously, but it's interesting to see. So let's imagine to keep the example of square lightning bolts and the shape that I drew in the first diagram. Let's say we have a class, a struct square, and another lightning bolt that both have a method draw that does a different thing, and we define use a compilation variable to define what shape means, and we run the program by compiling it with the variable. Then we get this result. And if we compile the program without the variable, then we get another result. This is polymorphism. It's polymorphism that's being resolved at pre-processing time. Not to say you should do that all the time, even though that can have some applications, but it's just an illustration that there is more than virtual functions in polymorphism. Now, if we move into compilation time, obviously there's the option of templates. I'm going to go a bit fast at the beginning of the keynote because there are things that are fairly basic C++, so that we get more time to discuss the meaty stuff. So if we've got a template with various classes that we pass in, then we get compile time polymorphism. The draw function that gets executed is chosen at compile time. Now, there's also polymorphism at link time, surprisingly. If you consider, if you think about what's happening at link time, we've got several files that have been compiled. Say the caller of the draw interface and one implementation of the draw interface in square .o file. The linker binds the two files to connect the function call and the function implementation, and that builds an executable. Now, if we had chosen another file than square, if we had chosen lightning bolt with another implementation of draw, we could have had another executable, and this is polymorphism. This is polymorphism that is resolved at link time. And finally, there's the classic inheritance and virtual function that is resolved at every call. So we've got an interface, inheritance, virtual function, override, the classic pattern. It's important, I think, to realize that this is the polymorphism is resolved at runtime, but it's resolved every time a client calls the interface. And this is extremely powerful because you can swap out at runtime the implementation and have a new implementation depending on something that happens at runtime in the application. Now, this is powerful, but it has a cost, right? So if you don't want that cost, perhaps you want to consider having a less powerful polymorphism that fits your needs. Let's see an example of that idea. Think about mocking in unit tests. You know, by mocking, I mean when you have you want to put some code in the test, but your code has some dependencies that for some reason you don't want in the test. Perhaps it's the UI, perhaps it's the database, perhaps it's just complicated, and you don't want it in the database in the unit test, then you can represent this code by an interface that has the same interface as the actual production code, but it's behind this interface. It's another implementation that's much simpler. Let's say that's mocking. There are various definitions of mock, stubs, fakes, whatever. But let's say this is what we're going to talk about. So we've got the class we want to test. That's called tested class. It uses another class that's called production argument. And production argument is what we don't want in our test, because it's, for some reason, it's complicated and we don't want it in our test, or it's slow to run, for example. What to do about it is the classical refactoring pattern to enable testing here is extract interface. Extract interface consists in introducing an interface that has the same syntax as the class you want to get away from test. And you have two implementations for that interface. One is the production argument, the original one that has the production code that you don't want in your unit test, because what you want to test is the production code of tested class. And another implementation especially designed for the mock. Let's call it mock argument. This is the classical pattern. And this is runtime polymorphism, which means that every time in the test or in production, every time f is called, every time do something is called, there is a polymorphism resolution with the cost that it incurs. That cost might be a problem, or it might not be a problem, but in any case, it's weird in terms of design, because when you write your code, you know that you're in the test or you're in the code. It's just not the same part of the code base. Why wait at runtime when you're on client side to make that decision? It just doesn't make sense. So now that we've seen that there are other polymorphisms before runtime, perhaps we can use one of them. The first one that comes to mind is perhaps compile time polymorphism, because those are the most famous polymorphism, runtime and compile time. So let's think about compile time. At compile time, we will have to use a template, right? And the interface will be implicit. Let's say we're not using a concept for this particular use case. And we'd have production argument, mock argument. All good. We have compile time polymorphism, and we no longer make that decision of resolving the polymorphism on client side. One problem with that is that you would have to have the code in the header file, because it's a template. If it's not a problem, then all good. But sometimes you just don't want to expose your code for various reasons in the header file. So what to do about it? It's not simple, but there are ways to get away with that. One way to do that is explicit instantiation. So let's say we don't put the implementation of the function in the header file. We just leave the declaration, and we explicitly instantiate. It's sort of like declaring the template for one specific type, both production argument and test argument, and we do that in the CPP file. And when we do that, the compiler will instantiate, and compile both production argument and tested argument, and it will include their code in the CPP file. So that will be just like regular function, not template, and we can just have the declaration in the header. Now, the problem is, if we do that, then we would have production arguments in our test binary, right? Because the tested class.cpp, which is the code we want to test, would be in the test binary, and we would have a trace of production argument in the test binary, and that would be a linker error, and we would be back to square one. So we need to find a way to get this bit away from the CPP file, but still make it available for the production binary. One way to do that, it's not simple, but it's called what I call the Chinese wall. The Chinese wall consists in having the header class, the header file, the CPP file. So the header just have the template declaration. The CPP file doesn't have anything about instantiation of the argument of the template. The instantiation is made on a separate file, on a separate CPP file that includes the CPP file of tester class. And the code you want to link, the code you want to add in your build files is the file at the bottom, testerclass.temple.cpp, because it has everything. And this is what is in your production binary. In your test binary, on the other hand, you have a symmetric file with just the explicit instantiation of the test argument, and they never are in the same binary. It's like a separation, like a Chinese wall. Right? There's a production binary on the side and a test binary on the other side. If this went a bit too fast, or if you want to get more details about that, I've written an article about this technique that you can access at this address, bit.do/Chinese wall. Now, if we summarize what we've seen so far, we've seen that for mocking, we have the option of virtual functions at runtime, which is the most common one. And we could have the more complicated Chinese wall at compile time. So if we need that, we can have it, although you may not want to have this as a first option because it's a bit more complicated. How about preprocessing and link time? Well, it turns out that there are options to do mocking with link time polymorphism. There's a library which is called fseam that does exactly that. This library will make everything for you to modify your build files with some scripts and your code as well, so that you can have polymorphism at link time to do mocking. And there even is a library to do mocking with pre-processing polymorphism. It's called Boccara. And to use it, you have to put some hooks, some macro hooks in your functions that you want to test, so that the Boccara library creates all the machinery to do mocking with pre-processing polymorphism. I think this is very interesting because it shows that even for mocking that most of us do with virtual functions at runtime, there are other possibilities, right? Which all have their trade-offs, but there are some polymorphisms at different times at runtime, and that we can use, for example, for mocking. Now, this pre-processing polymorphism, it's defined in the code, right, with hash define, for example. For compile time, it's also defined in the code with templates, for example. For runtime, it's defined in the code with interfaces and inheritance. But for link time, it's not defined in the code. It's defined in the build files. We're not going to get into the build files. We're only going to talk about code, but this shows 2 dimensions in polymorphism. There's one dimension which is the time, right? The moments of processing of source code from its writing to its running, right? So that's sort of like the time axis. And there's a new dimension, a binary dimension, being in the code or not in the code. So if we plot that, there are dimensions in polymorphism. And we can wonder, are there other dimensions in polymorphism? Well, there is one at least, which is dispatch. Let's explore that. By dispatch, I mean resolution of polymorphism. I generally use the word resolution, but dispatch is the same thing. It's just choose one of the possible implementation that will end up being executed. Because with polymorphism, you have several possible implementations, but at the end of the day, only one gets executed for a given call. So there's a choice to make, and there's a moment for that choice, right? Now, let's focus on the choice itself and not so much on the moment. So just to see what kind of choice is happening, let's imagine this very simple polymorphic structure with an interface and two implementations. And we have a client side, call side, sorry. And when we call that function, one of those pieces of code is going to be executed. The decision is based on the dynamic type with or the machinery of virtual pointers, virtual tables, or the virtual things. So depending on the type, it's going to be routed either on Square or on Lightning Bolt. And this is dispatch based on one criterion. It's called single dispatch. But we could imagine having several criteria, like two type criteria. That would be double dispatch, or in general case, multiple dispatch. You may have heard this phrase, I certainly have heard it, C++ doesn't have multiple dispatch. Some languages have multiple dispatch. I believe that Smalltalk has multiple dispatch, but C++ doesn't have multiple dispatch. Is that really true? Well, if we think about runtime polymorphism, indeed, C++ doesn't have multiple dispatch because there's only one type that's being resolved during a virtual call. But how about the other moments of resolution in C++? Let's take this example. So for the example of multiple dispatch, I'm going to take the same examples as Scott Meyers did in more effective C++ item 31 about multiple dispatch. The example he uses are space objects. So there are objects in space which can be of several types, and they can interact with each other by colliding, for example. And depending on what is colliding with what, there will be a different behavior. Let's have a look at this code. We have some template function that take types as parameters and do various things depending on the type. And we have the first line here, the first function here, that would swap around the types just to make sure we don't have to implement twice the same code, right? Because if an asteroid collides with a spaceship, it's the same ship. It's the same thing as a spaceship colliding with an asteroid, right? Now, if we have a call side with two types, then the compiler would resolve those two static types to make its decision about which code to invoke. And this is double dispatch. So there is double dispatch in C++. Another example, if we use overloading, right, with same thing, spaceship and asteroids, and we have a call side that passes to space objects, the compiler would use the two static types of the two objects to make its decision. So it's, again, double dispatch. So there is double dispatch in C++, and there's also multiple dispatch. If we had three or more parameters or template parameters, that would be the same thing. So we have multiple dispatch and templates, and multiple dispatch and overloads. What else do we have in C++? Well, in preprocessing, I don't think there is multiple dispatch. I mean, I haven't found it if there is any. And for link, I still haven't figured out what it means to have multiple dispatch at link time. Now, if we go back to runtime, we say that C++ doesn't have multiple dispatch. Is that really true? Well, this is, strictly speaking, it's true, but there are ways to emulate multiple dispatch at runtime in C++. This is what's done in the visitor pattern. So the visitor design pattern consists in having several kind of operation and several kind of objects, and the operations can work on the object. And we want to have a generic call side that has abstract operations and abstract objects, and applies this abstract operation on the abstract object. Call site that would look like that. So X, Y, and Z are operations, A, B, C are objects. The visitor design pattern has this structure. There is in the call side a virtual call on the object. So there's one virtual resolution. There's one resolution of runtime polymorphism, and inside of each object there's another virtual call on the operation. So it's like two successive single dispatch to emulate a double dispatch. Another interesting case of double dispatch is the following. So let's have a look at this code. We have A and B, which inherit from X. If we have two objects of type A, A1 and A2, and we have references on them through X, their base class. Consider this last line of code, the assignment. Does it compile? What does it do? What should it do? I'll let you maybe a few seconds to think about that in your head. Does it compile? It does. It compiles fine. What does it do? It assigns. Basically it calls the assignment operator of X. So it would probably assign whatever is in X, but not in A. And what would we expect it to do? Well, probably to call the assignment operator in A to assign whatever is in A, because we have two objects of type A and we want to transfer the data from one to the other. A different case, if we have an object A and an object B and we take two references of X, both objects, and we assign one to the other, same thing. Does it compile? What does it do? And what should it do? The answers are it compiles fine. What it does is the same thing. It assigns whatever is in X. And what should it do? Probably, well, it's difficult to answer. Perhaps it shouldn't do anything, or perhaps it should somehow create an error. Let the user know that something like that should not happen, or perhaps it should not compile in the first place. But assigning just what's in X is probably not what we want in most cases. Right. So how do we handle that? I mean, it's quite a basic use case. I've encountered that in production code more than once. We have runtime polymorphism, and we want to assign one object into the other. And it's sort of like, it's a kind, I think, of double dispatch, right? Because we have two objects, and we want to take a decision based on the type of those two objects. If they are the same type, we want to assign them with the derived class, and if they are not in the same type, we want to not do anything and perhaps throw an error or an exception or anything, signal the error. How do we do that? Well, one way to do that would be to have a virtual assignment operator that both derived classes would implement, and they would both test, is the source that's coming in the same type as myself, in which case I would do the assignment, and if not, I wouldn't do anything. Or perhaps instead of not doing anything, we would handle the error, perhaps throw an exception or a set, or I don't know, whatever. And if you have more than two derived classes, this doesn't scale really well. I mean, it doesn't even scale with two classes. This is disgusting. So what can we do to make this code more compact and in fact focus on what matters in A and B? Because all the life cycle of the classes, you don't want to worry about it in C++, right? You want it to work out of the box, the assignment operator, the copy operator, the structure, and so on, right, in most cases. So you don't want to see that at all. You want to see the business value of A and B. One way to do that would be to back off everything of that mechanism in a separate class that would be designed just for that purpose. Let's call that virtual assignable. And we would have A and B inherit from virtual assignable, and virtual assignable inherit from X. Then the virtual assignment operator would be implemented by virtual assignable, and the virtual assignable would know with the CRTP, it would know the type of its derived class. So it would know about A and B separately, and it would make the assignment by testing if the incoming object is indeed of runtime type of A, for example. And it would also have the error code at one place in the code, which is appreciable. So that would be the hierarchy for A. Now, we could also make the error handling generic, have a default implementation, for example, by making an asset, or provide any other default, and let the user provide another error handling function if it's necessary in this particular case. Right, now let's consider another example in the same idea. What if we want to do a comparison, like an equal or spaceship or whatever kind of comparison operator? We have the same problem, right? If we want to compare A and B, it should probably throw an error, or perhaps you would say that comparing an A with a B would always return that they're not the same thing. And if you're comparing an A with an A, then you want to call the comparison operator on A, and we could have the same kind of mechanism with a separate class that has all this code, and that lets A and B do their own thing, their own business value. Why not? The problem comes when you have several of those operations. I mean, those are operators, but you could imagine function. Class functions instead of operators, so the list can grow as big as we can imagine. So how can we combine those? Well, let's focus on just one part of the hierarchy because it doesn't change anything. Just to have one thing on the screen. We could think about having a multiple inheritance, inherit from virtual assignable and from virtual comparable. But when we draw it, it draws a picture that freaks me out, right? This is the diamond hierarchy, and I don't know. You don't want to get into that, probably. I mean, it creates all kind of problems. So let's try and find something different. Another way would be to have a single inheritance, but with something that would somehow combine all the virtual assignable, virtual comparables, and other classes. So this is perhaps the interface we would like to have. So that would be one way of doing that in terms of hierarchy. So we have the hierarchy at the middle, and the code of inherit with would be at the top of the screen. That's the entire code of inherit with, just to implement this hierarchy. So that would be inherit with just one skill, for example, virtual assignable. And if we want to have more than one, we can insert it in the hierarchy, right? With a variety pack arguments with inherit with inheriting from the other inherit with. Well, if this also went too fast and you want to dig into the details of, there are more details of implementing that. I've written an article about that too, that you can check by going to this link, bit.do/inherit with. But anyway, that's a way to do double dispatch on this specific case in C++. Now, there's another kind of double dispatch in C++. It is the one that's described by Scott Meyers, fantastic series of book, in particular More Effective C++, item 31, about the asteroids and the spaceships. This is not exactly the code of the book. I've changed it a little, just to focus on the point I want to make. But essentially, it's not the same idea. So we have a game object that should have a virtual destructor. I forgot to put it. Sorry. With derived classes, and we would have a way to declare how the various combinations of derived class would interact with each other. I've also changed the code because I've put some lambdas which weren't available by the time More Effective C++ came out, and that's also a way I changed the code a little. So imagine we have this collision functions where you can register functions, right, by sending lambdas associated with template types. So you like register function asteroids, and it would say that's what happened. That's what happens when two asteroids collide with each other. And same thing with the other types. We're going to see in a minute how this is implemented, but I want to focus on the interface first. And imagine we have this implemented, and we have two space objects that collide with each other. Then, then we would call the call function that would invoke the correct function given the two incoming arguments. Note that we passed in template types, and what comes out is a runtime polymorphic resolution. So let's see how this is implemented. So the idea that Scott Meyers wrote about, it's to store the type info, the runtime type information of the given types, of the pair of types, and associate them with functions. So for any given pair, there's an associated function. We have our register function that allows to pass in some functions. So we pass in with several types, and we assign the lambda, which is collision function, to the in the map with a corresponding to an entry of the two pair of type IDs. That's about it. There's a call function that makes a lookup in the map and calls the function, and that's about it. There's just one more thing to swap the parameters so that we don't have to write spaceship asteroid and asteroid spaceship in the definition. It's just if we didn't find it in the map, then we try the pair the other way around. And all this code allows us to first register the function by passing the type, sort of decaying the type into type IDs, storing the type IDs in the registry, and when called, looking up in the registry the particular runtime type that are coming in the call function. And that's what would be printed by this program. So C++ doesn't have multiple dispatch at runtime. Is that really true? It's strictly speaking, it is true, but there are ways to emulate it with visitor, with virtual assignable and all that goes along with it, and with the map that associates type info to functions. So in our bigger picture of polymorphism, where we saw the axis of time, there's the second axis of dispatch. We have single dispatch, we have double dispatch, we have multiple dispatch, and we have seen quite a few points, quite a few dots in that space where there is a possible solution in C++ to do various kind of dispatch on various times of resolution. Are there other dimensions? There are. There's another dimension, which is the nature of polymorphism. Let's get into that. If we say the phrase in English, f has a polymorphic parameter. So you have this call in your code, and you say there is polymorphism happening here. What does that say about X? What can X be? X can be a value of a fixed type. This is a bit perhaps questionable. By that I mean, imagine X is an int, like f expects an int, where you can have 1 or 2 or 42 or 100. That could be as many possible values for that type. And this is some sort of polymorphism, although it's really not polymorphism as we think about it. So we're not really going to dig into that option. But there are other options. X can be a value of various types. And this is exactly the kind of polymorphism that we think about when we think about polymorphism. It can be various types, and f could be a template function, or it can be various types that inherit from a base class, for example. But X can also be a function, right? Think about the SQL algorithms that take various kind of functions. Or F can be a group of functions. So we're not going to think about the first one. We're going to focus on the last three ones. Before getting into all that, let's maybe see what it means to have polymorphism on a group of functions. What does that mean, a group of functions? Still in the domain of square and shapes. Imagine we have a function that that computes a new color based on an input color. Let's say color are RGBs. It's just for the sake of the example. And we have compute color that takes a color and produces another color based on that input color. And we have another function that's associated with it, that's a log. So this log takes the input and the output and produces some logging about what happens in log computation. So those two functions go together, right? So we could imagine having polymorphism on such groups of functions. So we have one function with its log and another function with its other log function, and those could be two possible implementation behind one interface, and that would be polymorphism. So that's what I mean by a group of functions. This is exactly one use case I had in my code, although it wasn't about colors and rectangles and lightning bolts, but it's exactly the same structure. Right. Just to see an example of what we could have as a function and what example we were going to take for the rest of this part of the presentation. Let's say we have a function that takes a color and produces a color that's a bit brighter, and we have a log that says the color was brightened from this color to this color, and the same thing with a color that darkens. So we have two groups of functions here. Right, so we have those natures of polymorphism. If we think about our 4 moments of polymorphism and start with the preprocessing, do we have those natures of polymorphism at preprocessing? Well, for the values of various types, we have it, and that's the examples that we saw at the beginning with shapes. That's fine. Now, how about functions? Can we have polymorphism with functions? So let's take individual function, brighten and darken, without their log counterpart, just functions. Well, we can have the same mechanism with compiler option variable that we could pass, and that would change the function that is being called. So that would be polymorphism on functions based on preprocessing polymorphism. Same thing with a group of function. We can group functions into a type by having them as static functions. So we can have a struct brighten with static function and struct darken with static function, and we'd have the same macro mechanism where we would pass the brighten variable or not, and we would have the output that would be different, right? So color change here could be brighten or darken, and the color change compute color would be calling a static function inside of color change to compute the color, and same thing for the log. Now, an interesting thing with macros here is that we could also have that in namespace, which is nice, right? Because when you want to group functions, the most natural way C++ is to use a namespace rather than a struct, right? With everything that's included with namespace, for example, that you can define it at several places in the code, not all in a row. So namespaces offer more flexibility when it comes to grouping functions. So why not use namespace? Well, with macros, we can have the same calling size, right? Because the colon here would be in the namespace. This is completely not what we see on a day-to-day basis, and you can think about my macro disclaimer at the beginning. I'm not saying you should do that all the time, but it's interesting to see how far polymorphism can go. At compile time, value of various types, we've seen the example of templates with shapes and square. Now, if we have several options. In fact, if we look at this code, f is a template function and g is not a template function. It uses overloading, right? And it allows us to do polymorphism on values on various types. So we also have the option of overloading. About functions, or if we have our two functions, we could pass them as template arguments, right? Most of the time we pass type as template arguments with type name type. We can also, it happens that we can pass functions, function pointers, and this is the case since C++98. So the core side would look like that. We could pass widen or darken as a template parameter of functions. So that would be a polymorphic resolution of a function at compile time. And for a group of functions, we can group them in a struct as before with static functions and have them called by having a template parameter that represents the group. In this case, though, we can't do that with namespaces like we did with macros. Now, at link time, it's about linking with other files. We're not going to get into build files or a particular build system. We're going to stay in the code, so we're not going to get into the details of how to link, how to create polymorphism at link time. But by linking with other files, you can imagine that we can have either values with other types, as we saw in the beginning with shapes, or we can have functions by linking with various files that contain the implementation of one given prototype, or we can also have the same thing for group functions. And at runtime, we can have inheritance and virtual functions, obviously, but there are other options. So let's start with our classic inheritance, square and line enabled with shape. If we want to use polymorphism on those objects, it's a bit of a pain, really, in C++, because as soon as we want to do something to keep the object for a bit, then it gets complicated. For example, for this very simple use case of returning a polymorphic object, then we would have to create a unique putter, right? And this has so many drawbacks. It takes time to create it because we have to allocate memory on the heap, and it has pointer semantics, so it's more complicated. And it's just ugly, right? This prototype is the unique putter doesn't add any meaning. And in a prototype, all you want is meaning. So this is really bad. Same thing if you want to store polymorphic objects in containers, in vector, for example. You would have to store unique butter with all the problem that it involves. But there is another way. There is a technique that a reader of Fluent C++ has shown me, and I think this is the most beautiful C++ technique I've seen in years. I'm going to show it now. So this shape interface, we're going to rename it iShape. This is not the core of the technique, I reassure you. It's a debate whether we should have interfaces with I or not I. I don't really have a strong opinion on that, but in this particular use case, in this particular case, we're going to have an I. You will see why before. You will start later on, because we're going to have something different that's called shape. So let's update the inheritance lines. Now this is our shape. This bunch of code is going to be our shape. Let's analyze it bit by bit. Let's start with what it contains. So it has a storage of type any, std_any. Std_any came in C++ 17 and was in Boost before that, and it allows to do type erasure. Concretely, you can store anything, any type in a std_any, and you can put it back if you know its type with a sort of cast, which is called anycast, that we will see a bit later. So in shape, the purpose of this shape class is to store a shape, right? So in the any, we're going to put any kind of concrete shape, square, lightning board, whatever. And we are going to have another, a way to extract the concrete class out of the storage with this getter function. This is the prototype of a function that takes an any in parameter, which is going to be the any in the storage, and that returns an I shape. So the purpose of shape is to store a concrete shape and being able to provide it through its interface iShape. Just one more thing. To access it, we have this arrow operator that calls the getter function on the storage. All right? Now, this is how we're going to store the data in the storage. We'll have an incoming type that can be of any type because it's a template. And in practice, this is going to be the derived classes. So square, for example. So shape is a square. We're going to store this shape, this square, into storage. It's an any, not a problem. We can store anything in any. We're going to put the concrete class. And the beautiful part is this. How to create this getter function. So it takes an any, which is a storage, and it retrieves the object inside it, and it knows what type it is, right? Because we're still in the code of the constructor, and the constructor is a template, and it knows concrete shape. So we know that in the anycast there is concrete shape, right? So we can extract it safely. This is very simple, right? What's beautiful, really, in terms of C++ here, is that this concrete type, which is known only during the call of the constructor, it's somehow preserved later on, after the constructor is finished. It's preserved inside of the lambda. And I think this is one thing that lambdas allow to do and that no other C++ construct allow to do, including functions or all functions objects. The lambda allows to write implementation locally by using the current context, which cannot be done with a separate function or function object, even if this context is going to go away, and in particular with the template type. Right, so that's why I find it really beautiful when it comes to C++ techniques here. Now, what is it allowed to do? Well, it allows to have this shape that represents any kind of shape, but without it being a polymorphic object. So we don't have to use a unique butter to return it. We can just return it simply. Same thing for storing it into a vector. When you compare it with the regular way, you would have to store it with a unique butter. Now in practice, if we compare the two ways of returning a polymorphic object from a function, if we look at the call side, we have shape that we create. This returns a polymorphic shape. Oh, sorry, there's a typo here. This should be I shape. It's not shape, it's I shape. Sorry, it's important. So we create a shape that's a unique butter of I shape, and we call draw with the arrow operator. And on the other hand, we call create shape, and we call draw with the arrow operator. So it's the same thing. Does that mean that it's all for nothing? Not really, no. Because this one on the right has value semantics, whereas this one on the left has pointer semantics. And value semantics, it makes everything simpler. If you want to copy, for example, create another shape from that shape, just do that. If you want to copy with a unique pattern, it's complicated. You would probably have to create a clone virtual function in the interface and implement it and make sure you don't get it wrong, and burden the interface with that. It's just more complicated. And that would also allocate memory on the heap and everything that goes with pointer semantics. This one is nullable because it's a pointer on the left, and this one is not nullable because it's a value, which means that perhaps there was a crash in this program. And so that, I think this is very different, right? The one on the right, even though it has the same syntax at call site, so many things are different. Just in passing, we note that the arrow operator doesn't mean or pointer all the time. On the left-hand side, it means a pointer. On the right-hand side, it doesn't mean a pointer, right? It was the case already with the optional, because you can get the value inside of an optional with the arrow operator, and optional is not a pointer at all. So yeah, it's just in case you had a doubt on whether this was a pointer because of the arrow operator, it doesn't represent a pointer at all. Right, now if we go back to this code of shape, in fact, there's not much which is specific to shape in this, because there's nothing written in the draw method or anything. In fact, we could use this for any hierarchy, right? If we just change the name and made them more generic, I shape would be the interface, shape would be the implementation, concrete shape would be a concrete type, and shape would be object. So if we change those names, we get something generic that we can use with any hierarchy. And to use it with our hierarchy of shape, then we would write this. And I think this perfectly illustrates what this construct means, right? Shape is one implementation of iShape. We don't know which one it is because it's polymorphism, it's runtime polymorphism, but it's an implementation of iShape that has value semantics. Right, so we saw that values of various types. We have the classical inheritance plus virtual, but we also that has pointer semantics. But we can also have inheritance plus virtual with value semantics. Now, there's one thing that we haven't talked about yet. It's variant, right? We know that variant has some relation with polymorphism, so let's dig into that. So let's say we have a variant that can be either one of two concrete classes. There's no inheritance here. I have square and lightning bolt that represent two shapes. I mean, two abstract concepts of shape. And we materialize this concept of shape with a variant. We're going to use the overload pattern, which is a classical pattern that goes hand in hand with variant. So if you have an overload, in a few words, it's a way to have several functions into one object, right? You can define, for example, several lambdas, and the overload would inherit from those lambdas and make them available with the using function colon operator, right? It's a full expression that has been made possible in C++17, which is also the standard where std variants appeared. So this is something that we can do with std variants. We're going to see an example just in a moment. Now, actually, so we have this draw method, and we want to have a behavior that depends on the actual type, the current type of the variant, right? So we use the overload pattern that groups those two lambdas, one that takes a square and one that takes a lightning bolt, and we pass that group of lambdas to std visits that will find which one of the types of variants shape is currently, and will apply the right lambda. I mean, this is what it looks like from the outside, at least. So std visit it calls the value in the overload, the function in the overload that that can take this type inside of the variant. But we said at the very beginning that polymorphism implied having an interface. In this code, I don't see an interface. So perhaps we can have a draw function that is implemented in the classes. But in our definition of polymorphism, we saw that we want to have a client code that is independent from the various implementations. Right, and in this client code, I see other implementations. Now, we can use a just one lambda that is itself a template with auto and call shape and call draw on that lambda. And now we have polymorphism because we have an interface and we have independent, and most importantly, independent client code. And you know that in this case we don't use overload, right? So that's one way to do polymorphism at runtime with std variant. It's runtime because the resolution is made at runtime because the type of the variant can change at runtime. How about having a polymorphic function? So if we take our example of computing new colors again, we can simply pass a function as an argument of a function. All right, so we can pass compute color, we can pass brighten or darken to f, that will take it as its compute color parameter. So f has, the argument of f is a function pointer. This is the syntax of having function pointer as an argument in C++. Or we can also have this, we don't have to specify that it's a function pointer of this type. We can say it to be any type that's callable with this syntax inside of f. You know that this is template, but at the end of the day, it will end up being runtime polymorphism to define which function it's going to use. When we write the code in pass function, then the template is going to be resolved into the type of that function, or lambda if it is a lambda. But at the end of the day, the the actual passing of the function is going to be at runtime. In terms of call site, that would look like that. Now, how about a group of functions at runtime? If we have, again, our brighten and darken structures with static functions to group functions into a type, we can simply, well, it's not so simple, actually. Let me do that again. So if we have a group of functions, like we say, with static functions, at compile time, that was simple, right? Because we could pass them in template functions or with overloading. But at runtime, it's more difficult because usually you'd have virtual member functions, and static functions are not virtual functions, right? So we could get away with virtual functions, but let's say, just for the exercise, that we want to have static functions. And maybe it's not just exercise, because for one thing, virtual functions have their own constraints, right? And also, if we want to have virtual member function and not static functions, it means that we want to have objects, right? And in this case, we don't want objects. We don't want instances, various instances of the same type. We just want group of functions, right? There's no instances in group of functions. It's just one group of function. So let's try and make that work with static functions. A good call site that we can try and aim for, it's the one on the bottom, right? So we would have this color change, which will represent the group, and call it on compute color or log. I think in general, it's a good thing to write the call site first. I mean, not just about polymorphism, not just about C++, and in all cases, I think it's a great practice to write the call site first to make it ideal, and then write the implementation that leads to expressive code. That was just a side note. Now we have this call site. How can we implement it? Well, if we want to have that syntax, then compute color has to be somehow a function inside of color change, right? It's not a static function because color change, it's not brighten, it's a different type, it's color change, right? So we have to have those functions. One way to do that is to have function pointers in color change and connect them to the static functions inside of the group of functions, right? So to do that, we can have this sort of constructor. It's not really a constructor, but it's a function that allows to fill some data. Let's call that create from. Create from would take a template parameter that could be brighten or darken, and it would extract the static functions and put them in the function pointers. And the call site would look like that. If we make that a little more elaborate, just to illustrate what kind of call site we can have with this technique, let's say that we're going to add another function. Say that a particular group of function can handle only a spectrum of color, and so we add that into our color change, and we create a vector of them, all the possible color change, so that when we have a given color, we can look for one that will handle it. And in client code, that could look like that. So we have one particular input color, 50, 50, 50, and we get all the possible color changes, and we do a findif in it, right? By calling color change dot handles, which calls the function pointer, which calls the static function inside of each of the possible color changes, and then we call compute color and color change on the iterator that came out of this search. So this is, I mean, regular C++, just to illustrate that how that will integrate with this technique of having static functions in in function pointers. I mean, brought into function pointers. So the advantages of that is that we would not have to use virtual functions. One, that would spare the some cost of the virtual functions, and two, that changed the semantics that virtual functions mean objects, and in our case, we don't want objects. We have the semantics of group of functions. That would be what is output, and if we change the color, we get a color that would be worked on by another color change, then we get another output. And in this case, one of the costs of virtual function that we don't have here is heap allocation, which can be a performance problem. I mean, it's, in my experience, it has often been a performance problem. I mean, not that it's often a performance problem in code in general, but when there is a performance problem, in my experience, it's often a heap allocation problem. So this technique allows to get away with runtime polymorphism without heap allocation on group of functions. So for group of functions at runtime, we have this option of a function pointer interface. So that was from natures of polymorphism. Now, are there other dimensions? There are other dimensions. For example, is the interface explicit or implicit? By explicit, I mean, is it written out in the code? And by implicit, it's not written out in the code. It just has to work, right? Think about templates before concept, for example. That's an implicit interface. So for pre-processing polymorphism, the interface is implicit. You don't declare a macro interface. At compile time, without concept, it's implicit. With concept, it's explicit. At link time, you link with other files and you don't declare an interface, it's implicit. And at runtime, it depends on various options. For inheritance and virtual functions, naturally, it's explicit because you declare the interface in the base class. For std variant, it's implicit. For function pointer, it's explicit. And for function pointer interface, it's also explicit because you write out the function pointer's prototypes in the, for example, color change object in our example. Another dimension, being closed or open. By closed or open, I mean, can you add new implementation without changing the calling code? That would be an open interface, and a closed interface would be that you'd had to change the calling code to add the new implementation. So macro is closed, right? Because if you want to have a new implementation, you have to add an else if a hash else if in the hash if statement. And by calling code, I mean not just the calling code, also the code in general, the code that handles the polymorphic resolution. For templates, you would not have to change the template function. It's an open interface. For overloading, same thing. It's an open interface. If you just add an overload, that works. If you link with other files, it's also open. You can add any number of files and choose between them without changing anything else. I mean, apart from the build files where you actually make the choice. For inheritance and virtual, it's open. You can add new derived classes. The std variant is closed because you would have to change the declaration of your std variant. You would have to add new types to it. For function pointer, it's open, and for function pointer's interface, it's also open. Last dimension, time of checking. We've seen at the beginning the time of resolution, when the choice was made as to which implementation to go execute. Now, there's another moment that's interesting. It's the time where you check that the function you are calling exists in the contract. For preprocessing, that's at compile time, because the preprocessor will happily replace whatever you put in your hash define, and it's only the compiler that is going to stop if the function doesn't exist. At compile time, it's naturally checked at compile time. At link time, it's also checked at compile time. right? Because that's the same thing. You'd have to have the function that exists, and that's declared in a header, for example. And at runtime, it's also checked at compile time. If you call, for example, a function in a base class, it has to exist at compile time to be called. I think it's not the case in all languages, but in C++ it's the case. So if we have a final look at our bigger picture of polymorphism, we saw the axis of time of resolution. We've seen the axis of dispatch, and we also saw the axis of nature. On top of that, we saw there's time of checking, and that it can be explicit or explicit. It can be in the code or not in the code. It can be open or closed. And this is just for C++ as far as my knowledge goes. Now, this bigger picture of polymorphism, I think it's valid beyond C++, in other languages as well, right? For other languages, there are some various times of resolution. There are some various granularities of dispatch, various values, and all those dimensions, and perhaps more of them. At least there are some other cases for those dimensions in other languages. I'm not familiar with that, so I'm not going to get into the details of that, but I know that some languages, for example, Java, if I understand correctly, has a specific time of resolution in some cases at the first call at runtime, and then it somehow changes the compiled code, and keeps with this particular implementation without resolving it every time. It's apparently an option. And on another axis, on nature, you can think bigger than values and function. You can think of servers. If you think about a microservice architecture, when you do a call between two services, there's some sort of polymorphism that's going on, right? You can swap out various implementation of one given service so that the call is routed somewhere else, for example. So the nature of polymorphism goes way beyond values and functions and pieces of code. With all that, the final word and the message I really want to get across, I want you to get away with from this keynote, is that there is more than one type of polymorphism. When you think polymorphism, perhaps before this morning you thought virtual functions and inheritance, but there is so much more, as we've seen during this talk. Next time you need polymorphism, think about all the options that C++ provides to you, or any programming language provides to you, and think about which one to use in your specific case to make your code the most expressive and the most optimized possible. Thank you.
Thank you for the great keynote. There will be some questions on Remo.